Welcome to another episode of the Agronomy Highlights podcast. I'm your host, Ryan Spellman, and I'm joined here with my co-host and colleague, Justin Brackenrich. Justin, how are you doing on this wonderful fall day?
Good, good. We've got some sunshine over here after some storms, so looking forward to talking weather. How about everything for you, Ryan?
Oh, we have sunshine after that last week of a lot of rain. People are finally able to get back into their fields. Starting to harvest is very quickly approaching us. I have a lot of soybean fields coming off this week in this area. So it's a really great time to talk about the weather. I mean, I think we start every episode talking about the weather, but this
That's just
time
the way it goes now, isn't it? Everything you do, it's always about the weather, no matter how you slice it.
right, and I think when I started this job, Justin, me and Justin were chatting, and he sent me a picture of his weather station, and I told him, man, I need to get something like that. And you said every agronomist needs one. That's how you start every conversation.
It is. I mean, I think the more you do this, the more you realize how localized or how different things can be in this conversation starter of I live here and I talk to a farmer that's a half a mile away and I got 2/10 and they got an inch and a half, right? And you really, Kyle, and we're going to introduce him in a moment and what he does with meteorology, but I think from most people's perspective is we don't recognize how quickly things can change with the weather in such a short period of time. And my weather station actually broke, and it took us about 2 days at the house to get a new one because it is just such an integral part of our life and looking at the temperatures and the weather and all of that stuff. So really excited to talk about this and happy to have Kyle here. So Ryan, what do you think? Ready to
Yeah.
get started?
Oh, I'm ready to get going. We'll have the real expert here to talk
There you go.
about the weather rather than just us saying what we're finding on our little dinky weather stations.
So I've had the opportunity to work with Kyle in the past doing some of my virtual workshops, whether they be for forage or crops days, crops conferences, stuff like that. And it's always great to have him in. So Kyle, why don't you introduce yourself and tell us what you do and how you connect to Penn State and the weather?
Yeah. Thanks for having me on here. It's just listening to you chat about things there off the top. It's weather unites all of us in some way, right? But it's for those of us in the field itself, we all are kind of passionate about it. You catch the bug early in life, and you sort of stick with it. So that's a little bit about my background is, when I was a kid, I always had a fascination with the weather a little bit, but it was actually a major tornado outbreak that occurred in southwestern Pennsylvania where I grew up back in 1998. That's actually what got me started in it. We were in the basement, cushions over our head, tornadoes heading toward my house, and all of us, I think, as meteorologists, have that sort of storyline. So you guys in the ag community certainly know how important weather is, but for those of us that get into it on this side of things, we all have a story. Most of us do of how we got into the weather. So that was sort of my how I became passionate about the subject, and then I decided to stick in state and go to Penn State since we have such a good meteorology program here. And got my bachelor's degree here and worked for the state climate office right after I graduated, and then stuck around for grad school and got my advanced degree and have been doing this ever since in the state climate office.
Great, thanks, Kyle. Yeah, it's the weather does unite us all, and it's funny you mentioned, coming to Penn State. I didn't realize until I was at Penn State just how much of a mecca for meteorology programs it is. I mean, we have the AccuWeather headquarters right around the corner here, and Pennsylvania is a really unique state to study the climate. And I'm sure, and we'll probably get that in a little bit here.
Yeah.
So can you give us, for our agronomy audience, we have farmers that listen to this, agronomists that listen to this. Can you tell us a little bit more about what a meteorologist actually does? And is there a difference between a climatologist, a meteorologist?
Yeah, it's a good question. So we're kind of a diverse group in terms of the meteorology community. A lot of Penn Staters, specifically because we have such a good weather communications program, a lot of our students go into broadcast meteorology. So it is sort of the classic what you think of as the weather person, right? That's on television or now internet, social media, those sort of things that they go into that line of work. But the industry is much broader than that. I think that's immediately what people think of as meteorologists on television. But so many work in the private sector. So places like We have students in Southwest Airlines. Of course, they need meteorologists on staff. The military hires a lot of our students. Mars Candy Company is one. So all sorts of private industry that need weather information that impacts their operation. So the private sector has many meteorologists on staff that and places you probably wouldn't even think of off the top of your head. And then, of course, the National Weather Service is another place where a lot of meteorologists as forecasters go to forecast the weather. And most people are familiar with the Weather Service, and some stay in academia. Now, climatologists, going to your question about that, we're a subset. We do a lot of the same work, but climatology is focused more on long-term weather changes. So that's how you differentiate weather and climate. Is climate is looking at how weather changes over long periods of time. So more than just a few weeks or even a few months. When you start to get into years and decades and centuries, when you're looking at trends and historical weather information, that's what climatologists do. So some of us work in the future projection side of things. We look at climate models and try to predict what the climate will do into the future. And then there's others of us in applied climatology, which most state climate offices fall under that umbrella. We focus more on real-time and historical weather information to put things that have occurred into historical context, but then also to just help out whatever industry or whatever sector needs weather information, to provide that real-time weather information so they can make decisions or support them in whatever they may need.
That's pretty cool. The scope of all. I guess I never really thought of how many private sector industries,
Yeah.
airlines need meteorologists on staff. And Mars Candy, if I heard you correctly, is that for
Yes.
like shipping purposes?
Yeah, well, I think it's partly the growth of, I think that it's the entire supply chain. So talking about the beans themselves, for chocolate development, the kind of weather that's going to be conducive for that, all the way up to shipping and the rest of the supply chain there. So it's everything. So that's a fascinating one of the fascinating examples. Yeah, it's like I said, things you wouldn't normally think about, but like we just talked about at the top, weather impacts all of us and it impacts everything. And so that's all sorts of industries need that kind of that expertise.
So, Kyle, I want to talk a little bit. One of the things that I find most interesting about your work
Mhm.
is the mezzanine network and all of the kind of satellite, well, not satellites, but all of the weather stations that are kind of spread around Pennsylvania, and this kind of interconnectivity that there are. And I don't think a lot of farmers or even general public knows that this data is available out there
Mhm.
and all of that technology. So I'd like you to kind of, what research projects are you working on? Like, what's out there for the public? How can other people know more about what we have as far as resources and weather stations?
Right. No, that's a good question. So the mesonet work we do is really important and crucial for real-time monitoring of weather conditions. So the term itself, where mesonet comes from, so it's mesoscale network. And in meteorology, we split up the atmosphere into different subgroups. So we call synoptic meteorology is kind of the overview of large scale weather systems that you would see on a weather map, on a weather forecast, the big lows and high pressure centers and the big fronts that you see on weather maps. And then what mesoscale is, it's actually the smaller scale weather features, talking about things like snow squalls and lake effect events, or squall lines from a thunderstorm that they may form along a front, but these are really narrow, really intense thunderstorms that pass your house in 10 or 15 minutes and then they go away. So, and we know you've experienced it, right? Those really intense bursts of precipitation and then it stops. Well, you need to have plenty of weather instrumentation to be able to capture what's actually happening at any given time. So what mesonets are designed to do, you want to have a bunch of weather stations installed across whatever region you're interested in. Here we're focused on Pennsylvania, the state of Pennsylvania. So we wanted to install high quality weather instrumentation across the state to try to capture those rapidly changing weather conditions that'll impact every single sector, right? Everything from transportation to ag to emergency management, and that's why we developed this mesonet. So this all got started actually. So there's two different websites that I manage in the climate office. One is the Keystone Mesonet, which is keystone-mesonet.org. And that was actually funded by the Emergency Management Agency for the state PEMA. And they wanted to have a way to collect all existing weather networks from all of our state agencies, anyone that manages a weather network across the state. We wanted to collect that information, plop it on one website that's easy to use. You can visualize everything, and it's a really great way to get weather information in real time. So that's the first step in the process, was getting all the existing weather data together. And then the second part of this was Penn State actually, through a seed grant initiative, provided us money. Initially, I think it was $200,000 or $250,000 to install 20 weather stations, high quality weather stations across the Commonwealth campuses. That was our initial idea, was to put it at Commonwealth campuses in our Penn State network to have real-time weather information from there. Well, then Pima heard that we were doing this and decided that they wanted to revamp an existing weather network that they had to monitor flooding. And so they decided to put up some money for us to expand that network from 20 stations to 30 additional stations. So that's all part of our, what we call the Pennsylvania Environmental Monitoring Network, or PEMN for short. So we're going to be up to, probably by summer of 2026, we'll be up to 50 high quality weather stations. So we're getting close to one per county. So that'll be fantastic when we get all of these sites installed. And just like we talked about, that would be having that kind of dense network to capture some of those high impact weather events. That's the whole purpose of a mesonet. So that's kind of a little bit of background on where this got started and why we're doing it, because we're trying to gain real-time information about some of those high impact weather events that don't last a long time, but they can be very, very dangerous or very impactful when they do happen.
And so where I'm at, I'm in Fayette County this morning,
Uh-huh.
and we were talking before this started. There is variability between, here and a half a mile or something. But I can get on here and I can look at the what is this? The Fayette campus, right? And there is not only temperature and humidity, it gives me precipitation. But from the farming community, the interesting part is we can also see solar radiation. So when
Yeah.
we think about our plants, we can see how much of that actual energy is being there. We have soil temperatures and we have soil moisture, right? So like all of
Yeah.
this is, and I'm not saying it's going to be perfect to your farm, right? But it does give you an idea of kind of what's going on locally, right?
Absolutely. Yeah, absolutely. And that was one of our key stakeholders in this when we were discussing developing this network. That was one of the things we were really lacking in the state, was good soil property data. It's hard to get soil temperature and moisture, and I'm sure you guys are aware of this. It's really hard to find good quality data for that. So that's why we wanted to have those sensors on our environmental monitoring network sites, because that's something that's very, very important. And especially for the ag community, but even solar radiation, like you were talking about earlier, there's a number of different applications for that as well. So we tried to get instrumentation on these stations that were just that, filling in gaps in data that we didn't have before, or that other weather networks really didn't provide that kind of information. So we wanted to have some of those things, because it comes in handy, and it's extremely useful.
Yeah, looking at this map, there really is a good density of weather stations to pull data from. And like you're saying, traditionally we always talked about a lot of weather stations being at airports, and how
Yeah.
from a farming perspective, you need to take that data with a grain of salt, because they're on a hard top, right? So and it might be a little hotter, a little drier. So it's really important to have as close to your actual microenvironment as possible, in a way to collect that data.
Yeah, no, exactly. And representativeness, that's always something we talk about, is, there's only so many weather stations you can have, but obviously where you site them, where you put the instrumentation, is going to make a big difference. And you guys talked about it earlier about just how the weather varies so quickly. You can go down the road, or a half mile to a mile down the road, and you get a lot more precipitation or a lot less precipitation, or temperatures are going to be significantly different, because it might be a different soil type even down the road, or it could be cloudy down the road, and the sun's out where you are. So there's so many different factors that come into play that make just short-term weather changes significantly different from one location to another. So that's really the key, is trying to find areas where you can find a site that's representative of whether it's your field or your backyard or whatever it is you're interested in. Trying to get that data, that's crucial. And like I said, obviously you're limited. There's not, we don't have an infinite number of weather stations, but trying to fill in gaps is the key, to try to get a representative sample for as many users as possible.
Yeah, sure. So this is probably a good place to talk about some of the variability that we deal with in Pennsylvania.
Yep.
So for our Pennsylvania listeners, you're probably well aware that we have three kind of almost distinct growing zones to some level, and we have the southeastern part of the state that's warmer in general, the middle part of the state, which we kind of are in the ridge and valley area where I'm sitting right now, Kyle as well, I believe. And
Yep.
then Justin out in the western part that has its own climate, and then the northern tier is distinct as well, right? So we have a lot of different climates just in our state. Can you maybe talk about why it's so variable across the state? What are the major influences of weather patterns in our state and how they move, if that makes sense?
Yeah, no, absolutely. And you capture some of it there in the question. It's a really fascinating state actually to cover because it is a diverse state, and part of it is where we sit across the continental United States. So I'll get to our climate in a second, but if you think about throughout the entirety of the year, we can get severe weather, so severe thunderstorms, tornadoes. We can get the remnants of tropical cyclones. We can get, hurricanes that come up the coast and impact us. Certainly we're not immune to blizzards and East Coast snowstorms. So you name the season and we can be impacted by most of the extreme weather that runs the gamut of everything that's possible, really, that the atmosphere can throw at us. So that's one of the unique challenges of Pennsylvania too. But going back to your initial question about the state itself and how diverse it is. So that's kind of it. If you start in the southeastern part of the state, so obviously it's much flatter, lower elevation, and in meteorology, elevation and any chance for air to move upward is crucial to understanding what's going to happen. So where you're flat, but also closer to the Atlantic Ocean, where you have a nice body of water to provide moisture into the air. That's what really drives the climate in the southeastern part of the state. So a lot of the precipitation, especially during the cold season, where you can get coastal storms that develop, that leads to a lot of precipitation in the southeast part of the state. And then once you move up into, you mentioned the Ridge and Valley region. So this is a slightly drier part of the state, only because a lot of our weather comes from west to east. So when you think about air being forced upward on the west side of the Allegheny Mountains, so that you got the Lower Highlands in the southern part of the state and the Allegheny Plateau. So air kind of comes up the mountains on the west side of the state and it kind of wrings out the moisture. And whatever's left over gets to the Ridge and Valley region. And then sometimes you're able to pick up some moisture from either the Atlantic or the Gulf of Mexico to pick things back up in southeastern PA. But generally speaking, you get your wettest parts of the state are across the higher elevations of Western PA. And then you get into the central PA, kind of, slight minimum in precipitation, and then the southeastern coastal plain region. So really it's dominated a lot by the elevation and the terrain differences, and then how close you are to bodies of water. And then of course Lake Erie almost has its own microclimate because it's there on the lake, the lake shore right there at Erie, and how it impacts Erie, Crawford County, McKean County, those areas up there that get into lake effect snow in the cold season, and they generally stay cooler and cloudier for parts of the warm season as well. So a very diverse set of climates across the state, and again, most of it is driven by just how close you are to a large body of water, and then how high or low you are, and what's your surrounding terrain look like.
So Cal, I have stumbled onto the Köppen climate types. Is that a familiar word?
Yes.
Okay. So interestingly enough, this is like this color-coded. If anybody's not familiar, I would encourage you to look at because quite interesting. But it's this color-coded system of climate types that kind of shows everything that he was just mentioning about the northern tier and the ridge and valley and the coastal. What I find most interesting is looking at some of our paperwork where we talk about corn maturity types, soybean planting times and their maturities, small grains, and even to an extent, the Pennsylvania drought monitor that we're looking at right now almost follows this like kind of a T shape that comes up right through the Somerset, Bedford
Yep.
area and kind of tracks, right? I mean, I guess it should, all these years of science, but I guess I maybe never put this in perspective of how this climate is actually driving all of these factors that we're dealing with in agriculture.
Yep. Absolutely. And that T shape, that's a good way to think of it. That's your elevation right there. That's the elevation dependence that leads to a completely different climate. And you'll see that certainly going from so you're in Fayette County, but moving over to Somerset, you're in the higher terrain for a while, and then you start heading down pretty quickly into Bedford County. And so that's where those large variations, and not that much of a horizontal distance that you have to drive or go, that you can be in a significantly different climate regime strictly because is air being forced upward, which leads to cloud clouds and precipitation, or if it's on the other side and it's forced downward, that's generally what leads to drier conditions. And we call that a rain shadow effect. It's not as pronounced here in Pennsylvania as what you would see, like say in the Rockies. They get extreme rain shadows where you can go from extreme precipitation to almost nothing on the other side of the Rockies. So you see this same effect no matter where you're at, and no matter what mountain ranges you have. But that's really it. I mean, it's your climate's driven by that, and of course it's cooler in higher elevations too. So you get a cooler, wetter climate, all things being equal in those higher terrain areas, and warmer and drier, all else being equal in lower terrain areas.
So you kind of touched on one of the questions I wanted to ask you about was this year where I'm at, we saw a significant drought impact. We were hot, we were dry, kind of in this southwest corner of the state,
Yeah.
almost in this little kind of a off the side kind of bowl off of the higher elevation type stuff, or even moving to the north. How does that elevation affect or mitigate maybe some of this damage of drought? Does it stay more humid? Is there more potential for rain? Because we didn't, when our crop scouting and stuff, we didn't see that drought look nearly as bad in some of that northern area or even into New York. We've talked to people in New York and said they actually had excess of rain in some places.
Mhm.
And how does that affect some of that?
Oh, that's a great question. So I guess you could think of it as it mitigates it to an extent. The terrain can help to mitigate those effects because if anything, the mountains will wring out moisture. Any moisture that's available, it'll help to wring out some of that in higher elevation areas. So it can help mitigate drought in those circumstances. Now, some of the challenge we saw, because southwestern PA was one of our certainly problem spots this year with being really dry, and some of it really does come down to luck of the draw to an extent with the features that set up, whether it's large ridges of high pressure, or if you think of it the other way, if you're in easterly winds, so winds coming from the east toward the west, you can flip that whole signal I was talking about earlier, where now you're wetter on the east side of the mountains and it can get drier on the west side of the plateau, or the Alleghenies and the Appalachians. So that can happen if you're in that kind of regime for an extended period of time. It doesn't happen that often, but that can happen too. So some of it is the terrain can help to mitigate drought impacts, just because it makes it easier to precipitate. But at the same time, it does come down to what are the patterns that are setting up those persistent patterns that can last for weeks, or gosh, even months sometimes. It feels like in the warm season that can set up, that just leads to you getting very little precipitation in any given location, and it gets drier and drier. And some of that actually comes down to a feedback loop. So when you talk about drought, one of the issues is once you start to get dry, then the soils themselves dry out, of course. Part of the moisture content of the air is driven by evaporation of soil moisture. So if you start to dry out completely, you lose some of that potential you have to get moisture into the atmosphere to precipitate. So it can be a feedback loop where drier conditions get even drier and even drier because you just are losing the potential to evaporate moisture and water into the air to turn into water vapor and eventually clouds and precipitation. So you can get into those cycles where that's where drought can last for several years. We saw this in the Western United States several years ago, right? Where it felt like they were in drought for almost a decade. It almost was the case, at least for several years. They were in severe drought conditions, and that can happen where you just get into very persistent dry conditions, and then it's hard to break that cycle.
So, before we jump into actual a weather update and stuff, I have a question about maybe some terminology that might help us as we move into this, right? What is the actual term for drought? I'm sure there are benchmarks or things like that. What does that actually look like when we say we're in a drought?
This is actually $1 million question because
Okay, great. That's what
we
we're here for,
actually
right?
no, it's a very good question because it really depends on your perspective. We struggle in meteorology actually to define drought because it can mean different things to different sectors and different communities. Because drought could mean just simply, hey, we've been dry for a while and the grass is turning brown. For others, it could be, no, it's not really drought conditions until we've been dry for maybe 2 or 3 months, and now we're starting to see severe impacts to crops, let's say in the ag community. Or it could be a water resource problem. So you could be focused on, well, are there challenges with people having enough water to use for daily life? All of those things can have different thresholds for how much rainfall you really need and how dry does it have to be for you to get into drought conditions. So we really struggle with that drought monitor product. There's a lot of, I wouldn't say controversy, but there's a lot of conversation around how do you classify drought with one number essentially or one category? It's extremely difficult. So there's a lot of work that goes into that, but honestly, there's still not a lot of agreement. Obviously, some of it comes down to how much rain you get, but then it's how dry does the soils need to be? So you're monitoring soil moisture content. What are the antecedent conditions to drought conditions? Like, were you dry before you started to get really dry? Like, all these things come into play, and like, where your water resources low to begin with, and now it's easier to get in a drought. So it's a really good question, and there's no definitive answer, but like I said, you have different products that you try to tailor to different people and different communities and different sectors, but I almost think it's an impossible task to try to nail down drought as one number or one classification. The drought monitor is a great product, and it's a really nice, here's a one-stop shop to capture most of that information. But even that has its challenges when you're trying to boil all this information into one product like that. So we talk about this a lot in the climatology community, because it really is a challenge to define drought.
In extension, my favorite questions are the ones I get to answer with "it depends," right? Like,
Right.
and this is exactly one of those. Well, it depends on what your perspective of drought is. And that's a great answer to that question of some people see it very differently. And I guess the reason I asked that was you were saying that in the West, right, they were 10 years into a drought, what felt like a decade, where what point does that become no longer a drought, but a new climate?
Right.
Right. And we continually talk about this like volatile weather that we see extreme highs and lows, and like inconsistency is becoming consistent. But at what point do we start seeing this as climate and no longer inconsistent weather?
That's another good question. So we tend to use for our climate normals, let's say, which is kind of how we capture the baseline state of the atmosphere at any given time. Or, here's our long-term climate baseline. And we tend to use 30-year averages. Every 10 years we update this. So you often see products in climatology where we use a 1991 to 2020 normal. That's our last 3 full decades. And that's what we call the state of the climate at this point. Now, you bring up a good point, though. If you've been really dry or really wet for almost a decade, close to 7 or 10 years, can you make an argument that's your new climate regime? And that's another discussion we have all the time. And some people have pushed toward using a 10-year normal instead. If you've been at this state for 10 years, maybe you can go ahead and, flip the switch and call that your new climate regime, right? So there's certainly an argument to be made for that. I don't necessarily have a problem with that. And again, I think it may depend on the application, or it may depend on your perspective on what makes the most sense. But I think that 30-year average gives you at least, we know that the atmosphere can go into patterns that last for several years. So if you use a 30-year average, you sort of damp out some of the noise, and you can get a good baseline state. But 10 years, you can capture some of that, but you might be a little bit susceptible to noise where maybe you just were wet for 10 years and maybe it's going to dry out again. But you can certainly get into periods for multiple years. 3 to 5 years is certainly not a question, but even 7 or 10 years where you can get stuck in a certain spot and it's hard to get out of. And whether you call that your new climate normal, that's an open discussion for sure.
So this is just another pitfall of us humans wanting to put things in boxes, right?
Absolutely. Welcome to my world.
Right. So a professional putting things in box person, right?
Yes, absolutely.
I guess with that, maybe we can move on to our next topic. So we brought up extreme weather conditions, and I think coming off of a rain event, we've had, the last 2 weeks it was rainy for 10 days straight, it seemed here, and we came off with the remnants of Hurricane Helene, which, in parts of the country in North Carolina, Tennessee, seemed like a very unique hurricane. So can you talk a little bit about what's going on in the hurricane season this year? Is it a normal hurricane season? Why things followed weird paths, and how are we sitting precipitation-wise this fall?
Yeah, it's been kind of fascinating to watch this tropical season, and even going back to our local weather here for, here in the state of Pennsylvania, going back to like September to starting in early September, we had a stretch, at least in the State College. I was actually just looking at this morning, where from early to mid-September, we had a stretch where we barely had any precipitation. We had no measurable rainfall for almost a 12 or 13 day stretch, followed by a stretch of what you said, almost 12 or 13 days straight of measurable rainfall. So we went from no rain at all and bright sunny skies for most of it to all of a sudden it's cloudy and it's rainy every single day. And that in of itself was kind of odd, especially on the time of year. This September to October period is actually usually a cloud-free, drier time of year compared to the rest of the year. But then with the tropical season on top of this, what's been amazing about that is it was so quiet for so long. So even into the peak of the season, which is in I think the peak hurricane season date is like September 10th or 11th. So through that period of time, it was extremely quiet. And then all of a sudden, all it takes is that one storm like Helene to really kickstart things. And so that was really kind of an amazing event. And you could see, I mean, my concern as I was watching that develop was you could see that the impacts, there would be impacts along the coast. But then once that storm got up into what we call the mid latitudes, basically when you get into the US, and when it started to interact, there was a surface front kind of draped along the Appalachians. And like we talked about earlier, the mountains themselves will help bring out moisture as it is. So you had the mountains themselves plus a surface front, and you also had an upper level trough that was interacting with it. So that was one of the reasons why Helene sort of took a westward turn as it worked its way northward, which doesn't always happen. So there were a bunch of factors that led to Helene stalling out. There was high pressure to the north as well. So Helene came up the coast, it stalled out in the southeast, and kind of a worst case scenario for the southern Appalachians. And I'm not surprised. It's kind of horrific to see some of the scenes from parts of western North Carolina, most of the Carolinas, and much of the southern Appalachian region that's got serious impacts from this. I mean, they got someplace got 20 to 30 inches of rain in about 36 or 48 hours. Just extraordinary amounts of rainfall. That's almost a year's worth of rainfall in some of those places in about a day or two. I mean, you can't even, it's almost hard to even understand that. So yeah, it's one of those things that's when you see these kind of high impact weather events, it sort of wakes you up all over again when you know that the atmosphere of Mother Nature is capable of this kind of thing. But this was kind of like I said, a worst case scenario for the southern Appalachians. But yeah, it was kind of rare from the perspective that, like I said, you usually see these storms kind of head up north, they sort of speed up and then they curve out the sea, they go eastward or northeastward. And in this case, that didn't happen. Obviously, it stalled out, wrung itself out essentially over the southeast. Even here in Pennsylvania, we were on the very northern fringe of the rain, but we even got a little bit of rainfall across the southern half of the state from the remnants of the storm. So quite an event. It'll certainly be one to be studied for years and really a high impact event for sure.
Yeah, sure. I mean, I talked to Justin about this, but I was in Asheville 3 weeks ago. So where I
Wow.
was on a mountain biking trip. So, to see some of the scenes there are
Yeah.
just unbelievable. And seeing some of the places we were at just a few weeks ago, totally underwater. So for any
Yeah.
listeners out there, we hope everything's okay for you all and we can get to rebuilding. It's really tough. And so in the time of year we're in right now, is that what's driving a lot of moisture, a lot of rain events? Is the tropical, you use the word the tropical systems,
Yeah.
those
Yeah.
hurricane season? Is that kind of what we can expect for a rainfall?
Historically, that's generally how it works. So if you do dry out over the summer months, so some of that can be hit or miss. Whether you're under thunderstorms or not is a lot of the rainfall you get during the warm season. But then once you get into the fall and you get into the heart of hurricane season, a lot of times we sort of bank on the fact that we get some tropical system of some kind that comes up the coast and is able to give us some rainfall. Hopefully it's not intense enough that we lose a lot of the wind with it, but there's enough rain that we get some good soaking rains if it's been dry. So that historically is kind of a climatological average that we should see at least one or two remnants of tropical cyclones that gives us a good soaking rain. And like I said, you hope it's in places that have been dry and not places that have already been wet. So that can be another problem, but that can generally alleviate some drought conditions. And we've seen some of that with the systems that we've seen recently, and Helene helped a little bit with that. But yeah, that's really kind of what you bank on, because this time of year, like I said, from early September really through about mid-October is kind of a drier period of time where we have pretty quiet weather overall before we start to get into the cold season, get a lot more fronts, and you start spinning up stronger lows and all that kind of stuff once you get into the cold season. But this is where, this time of year you're really hopeful that, again, if you're dry, a totally different story if we're wet, but if we end up drying out a little bit over the summer, you hope you get a couple of soaking rains from a tropical storm to help help things out a little bit.
So I want to jump right into kind of what we're at here now and
Yep.
talking about the predictions for the fall. We've talked a little bit about this tropical system and this situation we're in right now. Um, One of the big conversations I have with a lot of producers is around this fact that we're not seeing a lot of snow in the winters
Mm.
and how that's kind of affecting some of our groundwater. And we've mentioned like water resources and how close that puts you to drought. I mean, I think that's kind of a problem for some areas. What are you seeing on is looking into your crystal ball? What the temperatures, the weather, the moisture, how do you think this fall and winter are going to stack up for us here in Pennsylvania?
Yeah, well, it's a good question, and this obviously introduces the concept, and if we weren't going to talk about it yet, it would come up El Nino and La Nina, right? So this is whenever we look into the crystal ball into, let's say, more than a couple of weeks out, that's we go back to these kind of global scale features that impact the weather. So for those of you listening that aren't familiar with El Nino and La Nina, it's basically just the temperature of sea surface temperatures over the equatorial Pacific. So sea surface temperatures in that central Pacific region that's either along the equator or just to the north or south of the equator. And basically when it gets really warm, when those waters get really warm in that region, it can impact it's a large enough impact that it can have downstream effects that certainly impact much of North America, but it can actually have a global signal that shows up across everywhere in the world that has some influence from a weather perspective, whether it's temperature or precipitation. And then La Nina, so El Nino is when it's warmer than average in that region. La Nina is the opposite, when you have a cold signal or colder than normal waters over that equatorial Pacific region. So when we look at forecasts for, especially in the fall like this, when we're looking into the cold season, we look at, okay, what are we in right now? What are the conditions like in the Pacific to try to give us some sense of what things are going to look like down the line. And right now, we're just coming out of, so over the late last winter into the spring, we were in El Nino conditions that started to transition back to what we consider neutral conditions, which just means waters are about where the temperatures are near the climatological average. So that doesn't really help us a whole lot with trying to gather information about what the next few months are going to look like. There are some indications, though, that we might head into La Nina conditions, which means those ocean temperatures are cool. So what that means for Pennsylvania and a lot of our climate models that we look at when we try to make a forecast like this, they're hinting at the fact that temperatures don't have a strong correlation with El Nino or La Nina, but if anything, it looks like things are favored to be warmer than average over much of the cold season, really from November through March. So I would anticipate that we end up over that 4 or 5 month stretch through the start of spring next year, let's say, will be fairly mild. I wouldn't be surprised if that's the case. In terms of precipitation, so the one thing that El Nino and La Nina do impact in the cold season is where storms tend to track. So if you think about the jet stream as sort of a railroad track for storms, that's the way I like to think of it. That railroad track can actually move depending on which signal you're in, whether it's El Nino or La Nina. So during La Nina events, we tend to get our storm track where storms cut up through the northern plains, through the Great Lakes, and then they cut sharply up through the interior parts of New England, which what that means is you tend to dry out or you don't get as much rainfall along the coast or in southern and eastern Pennsylvania, but western PA is actually favored to be wetter than average, not necessarily snowier than average, but at least wetter than average. So then the question mark is, are you cold enough for snow at any of these events? So that's what it looks like. A lot of the models are hinting at that. And then historically looking at La Nina events, if we do end up in a La Nina during the cold season, I think that's what we would be favored to have is a generally milder winter than average. And if anything, we're wet across Western PA and we're drier than average across Southern and Eastern PA. And like I said, the big question mark is everybody wants to know about snow, but that's almost impossible to tell months in advance of whether you'll have enough cold air in place for snow to develop. The only thing you can hope for if you're a snow lover, let's say, if you want some snow, is if these storms, as they cut up through the Great Lakes, when you get that northwest wind after a low exits, as those winds shift to a north or west direction, that can sometimes kick out the lake effect machine. And again, if it's cold enough, that can get you some of your snow that you'd like in parts of the lower highlands and then up near the lake shore. But But again, those are details that are just impossible to know months in advance. But that's at least what it looks like from a broad precipitation and temperature perspective. That's I think what we'll be looking at least based on the conditions we're looking at right now.
Kyle, I have a long time until I retire, and one of my goals is to understand the El Nino and La Nina. That's kind of on my bucket list of things to really get. And so, if there's anybody like me, I have included a NOAA link in our meeting notes that's got kind of a nice video of that and some things where he talks about the jet stream moving and stuff. But that is still kind of a term. I understand it on the veneer, right? I understand the temperatures being up and down, but there are so many layers,
Yeah,
or at least in my brain, of when the water warms up, how it moves the air currents and it moves water
right,
currents that is just hard for me to process. So
right,
we're
right.
very lucky to have people like you that can understand that for the people like me that just don't.
Right. No, it is certainly complex, and I'm simplifying it obviously by just saying it's a sea surface temperature anomaly, but it's actually much more complicated than that. It goes to overturning circulations within the ocean itself, and then whether the ocean is warmer or colder, that's what drives potential for convection, which is thunderstorms basically in that area of the Pacific. But those thunderstorms then they have what we call an outflow at the top where that's what changes the jet stream. So it all ties together, but it's a major piece of the puzzle from a global perspective that we've picked up on. I mean, it's kind of amazing that climate scientists, decades ago were able to figure out that, hey, this small signal, what looks like a small signal in the Pacific Ocean, is actually impacting things on a global perspective. So it is really kind of amazing that it happens like that, and there's a lot of pieces to it, but it's fascinating. It's one of the things I love to learn about, and it's a really cool mechanism. It's kind of you think of the atmosphere and the ocean, if it's a connected system, the atmosphere and the oceans, and the earth sort of breathes in and out, and so it takes in heat and it releases heat, and it's that breath in and breath out, that's what impacts our weather, and that's kind of the easiest way to think about it, is that sort of breathing in and out of heat.
Yeah, that's fascinating. Like Justin said, it's always been a mystery to me, but I think you got us a step closer to understanding it a little bit. And so, one more question on this before we move on
Yeah.
elsewhere. You mentioned that this La Nina pattern is going to affect how moisture is dispersed, and we might have a little bit wetter conditions in the western parts of the state, southwestern, and then drier throughout the rest. And you also said that now whether that's snow or not depends on the temperature. So where does our temperature come from?
So temperatures, so it is tied into somewhat into El Nino and La Nina, but like I said, it's less correlated. So the temperatures themselves are a bit trickier because it depends a lot on the jet stream undulation. So how far north and south the jet stream bends. That's the easiest way to think of it during the cold season. And can we get into if you think of cold air that's trapped over the Arctic as a means, as a source of cold air that can sometimes drop into our latitudes. So that's really what drives our cold season precipitation. So whenever we can get that cold air that's trapped over the Arctic for at least a lot of the season, and parts of Canada, whenever that can dip down and get into the United States, sometimes, I mean, we, from mild winters, we rarely ever get into the really cold Arctic air, but sometimes it can happen, and you tap into some of that really cold air. And the challenge with snow is, and this is what makes it impossible to predict, it's not just cold air that you need. You don't want an extremely cold air mass because it's usually pretty dry. So you need to have enough cold air, but still enough moisture, which means you're not super cold. You're just cold enough, you're sub-freezing, but you have enough moisture in the air that you can actually wring that out and get a good snowstorm. So it really becomes a clash between air masses. You need to have a lot of warm air to the south and east of wherever you're located, and colder air off to your north and west. And when those two come together, that's where you get your major snowstorms. And that's where it can be a real challenge to understand that. It's just when are you going to be able to tap into that cold air that can dip down from Canada and parts of the Arctic? And like I said, sometimes you very rarely ever get it in a winter. It may only happen once or twice where you get a really good Arctic air outbreak, but then other times you might dip into it several times in the winter. So that becomes a big challenge.
Interesting. So it's that is less predictable than, let's say, those influences of precipitation that you might get from the La Nina, El Nino.
Certainly, it's less predictable to try to capture whether you're going to get into the cold air when your main storm track is through the Great Lakes, let's say, in a La Nina pattern. It's hard to predict whether there's going to be cold air in place to change it over to snow, or or if it's just going to be warm and you're going to rain the whole time. Yep, absolutely.
Got it. So one other thing that's looking at where we are at this point of the season for an agronomic audience, right? One thing that we're really concerned about is your first frost date, right? And so traditionally, I guess we would probably consider our average maybe around in this area October 15th to 20th. Um, what are some of the climatic impacts that make your first frost date happen? I mean, it's a temperature influence, right? And is there any way to predict this time of year whether we're going to have one past what we usually do or earlier on?
There is on shorter time scales, though. You can predict it maybe a week or two out. You can see the conditions that are going to be conducive for getting relatively cold at night, where you're going to get into the 30s. So the conditions you need for that, certainly for your first frost and eventually your first freeze date, is you really need to have generally cloudless nights that have light winds. That's the conditions you need to get really chilly at night. So when you see those kind of conditions set up where you have, relatively cool afternoon temperatures, so you start off at a cool level before temperatures start to drop in the evening and overnight. So whenever you have that, and then you have a clearing sky, or generally clear skies, and again the winds aren't picking up and mixing temperatures out, you can get pretty chilly at night. So those are the conditions you really need. This time of year, obviously, we get into that fairly frequently. I was just saying earlier about this is a generally quiet time of year when, if you don't have tropical systems around or a front coming through, you can get ridges of high pressure that set up, and you can get relatively chilly at night. So those are the conditions you need to get those frosts and freezes. So in terms of whether it's going to be early or late, it's just a matter of trying to pick up on, are we going to be in a regime where you can get some relatively cloudless evenings or cloudless nights, and it's not going to be disruptive weather, cloudy and high dew points, that kind of thing. And that's what you're looking at to try to predict whether it's going to be early or late for frost or freeze.
So looking forward, do you have any predictions for a first frost? Or is
Yeah,
it too early to say? Do we see anything? It's October 7th now, so maybe
Right.
you can tell.
Based on what I'm looking at over the next week or two, I would say we're probably on pace to be near our climatological average. So most locations, there are parts of northern and western PA that generally get their first frost even earlier. Some of them have passed their average first frost date in the higher elevations, but in southeastern PA, where it is closer to middle to latter half of October, it looks like I think we'll be on pace to be close to our average. It's just a matter of when those high pressures set up at the right times. But over the next couple of weeks, I think it looks like there's some times where we should be able to get some less cloudy days and chillier nights where we'll drop into the 30s, and I think we'll see some frost and freeze conditions in short order.
so
Awesome, thanks. What's that,
that
Justin?
being
You go
said,
ahead.
um, thinking about that, so I'll tell you, I kind of cheated and I went to my weather app and looked out as far as I could look. And
Yep.
based on their prediction, it's well over a month before I'm going to see anything here below 30.
Mm-hmm.
That kind of brings me back around to this question of two parts. What good resources, or what are kind of the most accurate ways for farmers or producers to look at some of this stuff? And then my second one is, how far out can you actually trust one of these predictors?
You read my mind when you said about looking at 30 days out
Yeah,
in the
yeah,
future.
sure. Right.
So the first thing I'd say in terms of good weather information, I'm always an advocate for the National Weather Service, because these are the forecasters that are focused on the same region of the country year in and year out. They've been there and done that. They're professionals. So the National Weather Service, which is just weather.gov, if you're popping up the website, you can type in your zip code. It'll pop up a personalized forecast page for that location, and you can get all accurate information there. That's a great resource for getting weather information, better than what you would get on like a weather app, whether it's installed on your Apple phone, on the iOS system, or whatever Android weather app. That the Weather Service is going to be your best spot to do that. Now, when it comes to predictability, certainly you know, going out beyond 7 or 10 days is going to be a hazard no matter what. We basically hit, the way I like to think of it, there's sort of a predictability wall that really sets up at about that 7 to 10 days out mark. And sometimes it can be shorter than that, meaning that going out even beyond 3 or 4 days might be a hazard because we're not able to see the atmosphere is just in a weird state that's going to be hard to predict. Other times it might be predictable up until 9, 10, 11 days out, where you'll see some things on the models. And one example of this, an extreme example, was Superstorm Sandy that hits, you know, several, almost over a decade ago now. That was actually a storm that was accurately predicted to recurve into the Jersey and New York coastline 9 days out by one of our weather forecast models, which is pretty exceptional for a tropical cyclone moving into the mid latitudes and being able to predict that. So generally what I'd say is when you're looking at temperatures or precipitation, it doesn't matter. Outside of about 7 to 10 days, take everything you see with a grain of salt. In fact, I would say probably don't trust it at all. You're better off just flipping a coin to know whether it's going to be warmer or colder compared to what typically happens this time of year.
Now,
So,
in the
yes.
Cosmology Guild, are you allowed to say something like that?
Yes.
I feel like that kind of goes against the grain for you all, doesn't it?
Well, so it's the differential here is that what I'm referring to is weather forecast models that go out 7 to 10 days. Now, it's a different ball game when you're talking about climate models that are talking about using statistics and other features to go out decades into the future, and it's a whole different ball of wax. Different statistics, different physics come into play. So the predictability of those climate models compared to our forecast models are very different. There's overlap, obviously, in the physics and the math, but they're different regimes, so to speak, to think of it that way. But what I'm referring to is the day-to-day weather variations going out beyond about 7 days. It's almost, you know, like I said, you're hitting a wall where you're better off flipping a coin. But going out beyond that point now, I think what you're referring to also is the seasonal the seasonal forecast. That also is in a different bucket. So we have our climate models, our seasonal models, and then our weather models. And the seasonal models right now, I would say we're in our infancy with seasonal forecasting because we're so reliant on El Nino and La Nina and there's a couple other examples that are similar to El Nino, La Nina in different ocean basins. They're so reliant on those that if for whatever reason the atmosphere doesn't behave the way it typically does under those conditions, we really don't have any way to predict it. So that is a challenge when I'm making a seasonal forecast. There's a piece of it that's really, I wouldn't say guesswork, but educated guesswork. And the way I try to do it is I look at the seasonal models that use math and physics and the statistics, but then I also use what we call an analog method where I say, okay, we know what's been happening recently. And I've talked about this before in other venues, but we know what's happened recently. Let's say it's been a warm, dry summer across the Eastern US, just as an example. I'll go back in the past and say, okay, let's look at every summer that was warm and dry across the Eastern United States. And then let's see what the following winter looked like. Was there a connection? Is there any sort of signal that can show up from that? So we're using the past and just saying, okay, we know what happened in the past when these conditions set up. Let's try to make a prediction based off of that and forget about the physics and the math to an extent and just look at statistically what has happened in the past. So you're right. I mean, it is it may feel like I'm going against my own advice or my own techniques when I'm doing this, but it's a very, very big challenge to try to do seasonal forecasting and trying to predict things with any level of detail and the, you know, monthly to the seasonal, sub-seasonal time frame. It's just in an infancy. I think the science is in its infancy. Will get better, but there may just be, we may just have to admit at some point that there is a predictability wall that we hit, that we will never have a level of detail that people would obviously want at that seasonal or sub-seasonal timescale, that we will not be able to tell you next month that we'll have 7 days of rain and 22 days of dry weather, or, you know, during this week you're going to see temperatures like this or precipitation like this. That may never happen. We may never have that capability, and that's one of the challenges of our field. We try our best, but there is a level of, you know, you have to admit that there may be a wall that we hit at some point.
So that's where Puxatawny Phil comes in, right?
That's right. That's right.
Fill in that gap.
Yeah, he could take the blame every time.
Uh-huh, that's right. That's right. It wasn't you. It was the groundhog.
That's right. That's right.
So I think this is probably a good place to start wrapping up here. So I guess with kind of that, looking at some of these limitations of the seasonal predictions, and are there any tools, maybe not outside of just this seasonal prediction, but even on the shorter scale or the larger scale, are there any projects or tools that you're excited by that you think maybe you as a climatologist are working on currently that you're excited by, or things you see coming up with AI and a lot of technology? Is there anything that's going to make this a little better that you're excited by?
Well, that's you actually that last point you brought up, AI is a fascinating angle. If we are going to improve, in fact, that may be the way that we do it, because we've seen actually that there is some success already with. So not to get too in the weeds, but our weather forecast models that do predict out 7 to 10 days, they're using really complicated equations, and it's physics based. It's a math based system, and what we're finding is these AI models that are developed. Basically, it's a pattern recognition technique. So it's looking at what does the state of the atmosphere look like right now, and then that AI system is just looking at through pattern recognition using images basically of past forecasts or past weather events, and it's figuring out based on that what the future is going to hold. And there's been a lot of success actually already with some of these AI systems. I'd be fascinated to see if we start to develop these AI techniques for the seasonal time scale or the decadal time scale, it might actually be better than what we have now with our numerical weather prediction system, which is what we call the math and physics based system. So that I actually am intrigued by, because like I said, we're already seeing some success with that right now. And the beauty of this is too, with the AI systems, we have to wait right now for our forecast models for 4 to 6 hours is how long these models take to run. They're extremely complex systems that take forever to solve, even with supercomputers. Some of the largest supercomputers are used to solve meteorology equations. So these AI systems, though, can spit out forecasts in minutes. So the implications of that, I mean, there's so many things that come out of that if we do have success at seasonal timescales or like I said, even out decades that improve upon our climate models, there may be some windows of opportunity there to really improve our forecast. So I'm fascinated to see that from a climate office perspective. One of the things I'm excited about that we're working on, not really in the forecast side of things, but looking at historical weather information and current sort of situational awareness for the ag community. Actually, on our climate office website under our features tab, there's what's called the Agricultural Climate Center. And we have a lot of nice maps, growing season, degree days, precipitation charts. They're dated though. It's been a while since we've updated those sites. They're sometimes 15, 20 years old. So what I'm having some students do right now, and a couple of my colleagues, we're working on revamping that whole section to have nicer maps, updated weather information, so that you can have some really good information about growing season. So we talked about first frost, first freeze, last frost, last freeze. So all of those maps are going to be developed and have updated weather information. So I'm excited about that. We're going to work on that over the next 6 to 12 months and hopefully have something in place by maybe late spring of next year. We'll have that website totally revamped.
Excellent. Well, what was that website again? Can you say that again?
Oh, so this is our climate office website. So it's
Okay.
climates.met.psu.edu. And then when you're at that website, just click on the features tab, and then you'll see a list of different features we have. And I think it's right near the bottom of the list. It says Agricultural Climate Center, and you can click on that, and there's all sorts of useful links and information there you can play around with. And like I said, it's dated a little bit, but we're gonna work on updating that and make it better.
Well, that sounds great. It sounds like that will be a wonderful resource, especially for folks in the ag community. Finding some resources that they can really trust there. So I think with that, is there anything else where people can find you or maybe see what you have going on that we haven't already said? We'll include the climate met and as well as some of this other stuff that you put down. We'll include all of this in the show notes. So if you have anything else that people can find you at, feel free.
Yeah, no, absolutely. No, it'd be our climate office website and the Keystone Mesonet page that we talked about already. We also have an X account I have our students manage that, so they'll post some interesting climate tidbits. It's our PA Climate Office is our Twitter handle there. So you can or X handle, I guess it is now. So you can go ahead and visit that, and yeah, you can find all of our information at those websites.
Awesome. Well, thank you, Kyle. I really appreciate you coming on today. Like me and Justin said, this might be something we start to do once a year or in other parts of the season to just kind of get some information on what's going on in the climate for our viewers. And yeah, I learned a lot about how weather actually works and how hard it really is to predict these things. I think there's a lot of things that us as agronomists, as your just general human being, that you don't know, like how these weather models work, how they're interpreted, how hard it is to really say what's the weather going to be this winter. So I think we learned a lot here, and I think our viewers will get a lot out of this. So we really appreciate you coming on, Kyle.
Yeah, thanks for having me. And I will say, just to finish up, that some of the groups I love talking to the most are in the ag community, because you guys appreciate the weather probably so much more than any other group, because everything you do revolves around that. And so you guys also understand it, I think, better than a lot of people. You're most in touch with it, I think, than even some of us in the meteorology community do. That you're out in the fields all the time experiencing this. So I love talking to these groups because you understand it, you get it, and you know all the impacts of the weather and all the changes that you see. So it's really fun to talk to groups and talking to you guys too on this podcast. It's been great.
Certainly, yeah. I know for us, our farmers really rely on the weather. So, the first thing that happens during a rainstorm is every farmer is calling each other, "Hey, how much are you getting over in your valley? How much are you getting there?" So, really, everyone's so closely connected to the weather. So, it is great from our perspective too to hear from some meteorologists, because it is something we interact with so intimately. Well, with that, I think we'll end this podcast here. For our listeners, I hope you got as much out of that as me and Justin did. And we'll see you again for another episode of the Agronomy Highlights podcast.